This is Euclid Book 10, proposition number 26. Let's get into this, shall we? For medial area does not exceed a medial area by a rational area. For if possible, let the medial area AB exceed the medial area AC by the rational area DB. Okay, so now we're saying that we have this giant area right here of AB. So it goes A something B something up here. This whole area is going to exceed the area of AC, so it'd be ADC something here. Okay, so the great big area exceeds this area by DCB something. Okay, super great big area, this area. Okay, super great big area is going to be, it's going to exceed this area by this one. That's what he's saying. I think you got that. Okay. Now, we also have to say that this area down here we know automatically is rational. Okay? Very important. And let a rational straight line EF be set out. Okay, so now we're going to say that this line is rational. It's going to be set out. Okay. To EF, let there be applied a rectangular parallelogram FH. Okay. So once we make this, we're going to apply a rectangular parallelogram. Okay, this is a rectangular parallelogram, and it's going to be FH. So we draw this line, then we draw this rectangle. That's what we do. Okay. Now, the rectangle FH is going to have the same area as AB. Okay, and it's going to produce EH as the breadth. So, the area inside of this giant rectangle is going to be the same area as in this giant square, and this is going to be the breadth of this rectangle. So much for that. Okay. Okay. And let the rectangle FG equal to AC be subtracted. So, we're going to draw a line KG, and the area inside of here is going to be the same area inside of here. Okay? So far, so good. Therefore, the remainder BD is equal to the remainder KH. And when we say that BD is equal to KH, which we can, this is going to be equal to this. So, we've said this is rational, therefore this one's also rational. Okay. Since then, each of the rectangles AB and AC is medial, okay, so this great big area is medial, and so is this smaller area known as AC, the top part, okay. We now can say that. And if AB is equal to FH, okay, and AC to FG, so now we're saying that the area inside this giant square is equal to the area inside this giant rectangle, and we already said that this area is equal to this area. Alright, Therefore, each of the rectangles FH and FG are medial. G. We can now say that the great big area FH and the smaller area FG, they're both medial areas. Okay. And they are applied to the rational straight line EF. Okay. Therefore, each of the straight lines HE and EG. Okay, so now we have HE and EG. So now you know what we're talking about there. So this is a straight line. This is a straight line. This is a straight line. Okay. Therefore, each of the straight lines HE and EG is rational and incommensurable with EF. And this is by Euclid Book 10, proposition number 22. So, this line is rational, this line is rational, but there is no number that will measure the length of this whole line and this whole line, and there is no number that will measure the length of this whole line and this whole line. That's what they're saying. That's what Euclid's saying anyway. Yeah. And since DB is rational and equal to KH, therefore KH is also rational. Okay. This is equal to this. This is rational. This is rational. Okay. And KH has actually been applied to the length of EF. You say, well, I don't see that. Well, what is the length of KG? It's the same length as EF. So this whole area has been applied to the length of EF through KG. That's how that one works. Therefore, GH is rational and commensurable in length with EF. This is by Euclid Book 10, proposition number 20. So, this length is commensurable with this length. Okay. But EG is also rational and is incommensurable in length with EF. Therefore, EG is incommensurable with the length of GH. Okay? So that's by Euclid Book 10, proposition number 13. So, what they're saying is that there is no number that will measure both the length of EG and GH. That's what's being said. Okay. And as EG is to GH, so is the square on EG to the rectangle EGGH. Okay. So what they're saying here is, as the length of EG is to the length of GH, that's half of it. Okay, that's half of a ratio. Okay. So is the square on EG. So if you were to take the length of EG and you made a square out of it, okay, so all four sides of the square would be the length of EG, that whole area would be in proportion to the area contained by the lines EG and GH. So here's what you do. You would first take this length, make a square out of it. Okay, so all four sides of the square would be EG. There would be one area. Then you would take the length of EG and GH, and you would have a rectangle, and that rectangle would have 2 sides the length of EG, and the rectangle would have 2 sides the length of GH. And so the square area of EG would have the same area. Well, it would be in proportion, okay? So the square area EG would be in proportion to GH. So in other words, as this line is to this line, so is this area is to that rectangular area I was telling you about. You probably want an illustration. Okay, as this line is to this line, so is this area is to this area. And EG and GH represents 2 sides of a rectangle. Okay? There's your illustration. Okay, let me erase that, because now we can go on. A little less confused now? Good. Therefore, the square on EG is incommensurable with the rectangle EG and GH. This is by Euclid Book 10, proposition number 11. But the squares on EG and GH are commensurable with the square on EG, for both are rational. Okay, so if you were to make a square using the length of EG, and you were to make another square using the length of GH, those two areas would be commensurable. And they'd be commensurable with the square on EG. And twice the rectangle EGGH, so if you made a rectangle out of EGGH, and you did that twice, then the areas of both of those rectangles, if added together, would be commensurable with the rectangle EG and GH, because it's double of it. Okay. So, let's try this again. I'm sorry that we had to do it this way, but the way they've explained it would have you very confused. So what they're saying here is, if you were to draw two rectangles, and the two rectangles would have the sides of EG and GH, and you drew this rectangle twice, it would be commensurable with drawing the rectangle once, and that's because two rectangles added together would have an area double of one rectangle. That's what they're talking about. Got it so far? Okay. And that's by Euclid Book 10, proposition number 6. Now, why is all that important? Well, we're going to find out. Therefore, the squares on EG and GH are incommensurable with twice the rectangle EG and GH. So what they're saying here is that if you were to take EG and form a square out of that, and you were to take GH and form a square out of that, you can draw this up for yourself. I'd love for that. If you do it and you want to post it on YouTube and want to let me know, I'll put it in the description below. I will do that for you. Okay, so if you really want to go ahead and do this, go ahead. So now you have an area and all four sides are EG. You have another area and all four sides are GH. Then adding those two areas together, they would be incommensurable with twice the rectangle of EGGH. So in other words, you take a rectangle and two sides are EG, two sides are GH, and you double that area, that would be incommensurable with the first area. And that's by Euclid Book 10, proposition number 13. Therefore, also the sum of the squares on EG and GH and twice the rectangle EG and GH, that is the square on EH. Okay. So, now we got to put up this equation here. Okay, now we have let's start this way. Take a look at this equation. We first made a square and all four sides of it were EG. Then we made another square and all four sides of it were GH. Then we made a rectangle called EGGH where two sides were EG and two sides were GH. And then we multiplied the area of that rectangle by 2. Okay, so now we have this square area, and these two rectangular areas. All of this combined becomes, believe it or not, if you add all those areas together, whoops, you're going to get 1/3 of an area. Okay, so now, what did all that area form? Well, it formed so now we can take the length of EH and we can make a square out of it. So we have now another square, and all four sides of that square are going to be the length of EH. So all that area we were talking about a minute ago forms that area right there. Wow. And that's by Euclid Book 2, proposition number 4. So the area of the square of EH, which we have now established has been made, okay, is incommensurable with the squares on EG and GH. Okay, I bet you're confused. Let me make sure I got this right. So if we made a square out of the length of EG, and we made a square out of the length of GH, and we added those two square areas together, they would be incommensurable with the area of EH. That's what Euclid's saying. Wow. Okay, and this is by Euclid Book 10, proposition number 16. But the squares on EG and GH are rational. Okay? Therefore, the square on EH is irrational. And that's by Euclid Book 10, definition number 4. Therefore, EH is irrational. So now we're saying that the length of EH is irrational. But at the beginning of the proof we said that the length of EH is rational. Well, that's impossible. It can't be both rational and irrational at the same time. Therefore, 4 medial areas do not exceed a medial area by a rational area. Just can't happen. And now we've proven that. Whew. Aren't you exhausted? So am I. Alright, I will tell you more in my next video, so stay tuned.